Thank you, everyone. I've been introduced already. Let's start. Um, so, to understand why post-quantum cryptography is a big topic in the industry right now, we need to just make sure that people know what public key cryptography is first, because that's where all of this begins. So, public key cryptography is a little bit less complicated than it sounds. It lets you encrypt and decrypt data. For example, if you're using credit card information to buy something over the web, that needs to be encrypted and decrypted without people intercepting it in the middle. You need to be able to use public cryptography to sign and verify things. So, for example, you install a software package from Red Hat, you need to be able to verify that it is from Red Hat, and that is done through a cryptographic signature that Red Hat has provided. So, what are the components of that? Well, you've got a private key and you've got a public key. They're connected to each other. You sign things with a private key and then verify them with the public key that corresponds to it. I encrypt a message to you using your public key, and then you decrypt that message using your private key. Uh, the way all of this works is that the public key and the private key are mathematically related by a one-way function, and the mathematical relation between the private key and the public key extends to the signatures and the encrypted messages that are produced with those keys. So a one-way function, again, a little less complicated than it sounds. It's just a function that's easy to do one way and difficult to do in reverse. So, for example, if I asked you to multiply 89 by 97, a lot of you could probably do that pretty quickly with a pen and paper. Maybe you could even do it in your head. But if I asked you what are the prime factors of 8,633, without the prior knowledge of the previous question, you might be going to Wolfram Alpha and asking it, or you might be writing out a bunch of prime numbers on a paper and crossing them out using the sieve technique. Uh, so the answer is 89 and 97. But working that out is a lot more difficult than doing the multiplication. The widely used RSA system, which is a public key system, does basically that, but with much larger prime numbers, and that's part of the one-way function that it implements. The one-way function makes reverse engineering the private key from the public key computationally impractical, and this is important because impractical is different from impossible on a theoretical level, but impractical has been good enough for us so far. So, quantum computers are a threat to our one-way functions because they allow certain mathematical operations to be done more efficiently in theory than they can be done now. Uh, what you've got in a quantum computer are qubits instead of classical bits. And what makes them special is that they can exist in a quantum superposition. So you can have basically, um, you can have a qubit that is not precisely in a 1 or 0 state, but instead it's some scalar combination of states. Um, you can operate on values simultaneously using those qubits. This is actually not practical for general purpose computing. It does not speed up your video games, but future machines could possibly factor integers and solve discrete logarithms quickly. And this would cause a problem for the one-way functions that we talked about, because those are common components of one-way functions. So the moment when quantum computers are able to actually do that is called Y2Q or Q day. Now, the way we address this problem is with post-quantum one-way functions, and there's a bunch of candidates for it. I won't go through each of these. I won't even say that I understand each of these particularly well, but they pull from different branches of mathematics. They pull from lattice problems in linear algebra, um, and there are a few other techniques, but the lattice problems are the basis for the emerging post-quantum standards that are being pushed by the U.S. government cybersecurity agencies right now as a standard for the industry. But a good question to ask is exactly how soon is Y2Q? When is public key cryptography going to come down at the working of quantum computers, and when is everything going to break? Well, it might not be soon at all. So it turns out that we've got a timeline where you can see that it's developing not necessarily immediately. In 1994, there was an algorithm already for solving the RSA kind of one-way function, but it was not yet implemented because this was using theoretical computers that didn't exist. In 2001, um, some researchers at IBM were able to factor 15 into 3 by 5. In 2012, they were able to factor 21 into 3 by 7 at UC Santa Barbara. And in 2019, they tried to factor 35 into 5 times 7, and they had too much statistical noise to actually make that happen. They got the wrong result. So the thing about finding the results of these quantum calculations is that it's more of a statistical exercise than just reading off the result from a classical computation. And in 2023, there was a pretty comprehensive paper from UW-Madison where they found that this algorithm for breaking RSA encryption is basically unworkable when you get to numbers that are large enough that they're actually used for practical purposes in RSA, unless you do some kind of noise correction, because the statistical noise that is coming from quantum computers is too much in the way, and it will only get worse the more qubits you add. You need more qubits to get the calculations for these larger prime numbers. And when you get to the point that you have that many qubits, the noise is so much that it's pretty much insurmountable. Um, However, US government cybersecurity agencies are not waiting. They are looking to implement post quantum standards right now. So uh, in 2024, we got finalized standards that people could implement. These are basically replacing the previous public key cryptography standards. Um, they are still considering the pre-quantum public key security standards acceptable in their terminology through the end of this year, 2025. Um, so there are some mandates to implement um, the new post-quantum algorithms by the end of this year in certain sectors of the industry. And they want a complete transition to those post-quantum algorithms by 2035. Now you know post-quantum cryptography. Um, there's a lot that I left out, but some starting points for understanding more of this topic are here on the extra credit slide, and I can take a few questions.
Hi, thanks. So let's assume an optimistic development pace for quantum cryptography, quantum computers rather. What could we do today? Is there an RSA key length, for instance, that might keep us reasonably safe for some reasonable time period, such as the rest of our careers?
Yeah, so what you can do today is use post-quantum algorithms that have already been implemented. So that's the first bullet on this slide. The MLDSA algorithm and the MLKEM. So DSA is, I'm like blanking on the actual acronym right now, but that's for signing. KEM is a key encryption mechanism. So that's for like encryption and decryption. Um, these are based on standards or algorithms that were devised in academia, I think. One of them was called dilithium, and the other one was called Kyber, in references to Star Trek and Star Wars, respectively. But the official names for these are MLDSA and MLChem. So these are both implemented by a new PGP system called Sequoia, which is written in Rust, and it's developing pretty rapidly. It's developed by an independent team, and it's pretty good. They're working on integrating it with various kinds of hardware. But even if you use GPG, they have implemented something similar to MLChem. It's their implementation of Kyber, and they combine it with a like pre-quantum elliptic curve that is there in case it turns out that because we haven't tested these post-quantum algorithms for as long, if it turns out that they're not secure in some way, then we can at least fall back on this elliptic curve until Y2Q, whatever that is.
So what is it for someone who has like an application that runs behind a web server, let's say a bank? What do they have to think about as they approach this? Like what actions do they have to take?
Yeah, so it's probably not going to be an immediate issue, but in the long term, like we want to be implementing this stuff at the protocol level, like for SSL, DLS, for we want to be implementing these post quantum algorithms at that level before Y2Q. I think there's more urgency being placed on certain like sensitive applications, um, especially in like signing and verification. So on the back end, if you're running an application like that and you need to do like end-to-end encryption, or you need to do something that's not at the like network protocol level, then you could probably be implementing this stuff like now, using Sequoia or other emerging implementations.
Yeah, I was just curious if we can be doing anything at like the data level itself, like before Y2Q, because I know people are like data hoarding right now. Like, I don't know, I'm thinking like social security numbers or something. Can we like obsolete this data in some way where like it won't be useful after it's decrypted by post-quantum cryptography?
Yeah. So if this data is out there, like in theory, it could be broken. There's a computational cost, even when you're doing like quantum algorithms to break RSA. So there's a question of what data is worth an attacker cracking it, given the large computational cost. Um, there's also, with existing PGP keys, a revocation mechanism. So, this doesn't solve the problem of data that's already out there in encrypted form. Like, in theory, someone could grab that and then try to crack it later. But you can, for like signing verification purposes, at least say, I've switched to a post-quantum key now, and the pre-quantum key is no longer valid for verification. All right, thank you. I have, I think, the third talk in here as well. So see you around.
Let's have a round of applause for Dominic.